Okay, this is the third video on volumes of revolution cylindrical shells, and we're going to look at one more example. This is example number 4. We're going to find the volume of the solid bounded by y equals 1 over x, x equals 1, x equals 3, y equals 0, and I'm going to revolve that around the x-axis. First, we're going to use the shell method, and then we're going to use the disc or the washer method, whichever is appropriate. Okay. All right, so we're going to go ahead and do a sketch, and I'm not going to make my y-axis to the same scale as the x-axis just to be able to draw a larger picture to kind of see what we're looking at. So here is our region that we're going to rotate around the x-axis. Okay. And if we're doing shell method, we need to be parallel with the axis of revolution. So our represented rectangles of our shell need to be horizontal. Because they're horizontal, they need to be in terms of y. Okay. Now this has an added complexity in that the height function is going to change. Okay. So if we look at my representative rectangle there, the distance from that represented rectangle to the axis of revolution is simply y. Now, I have another representative rectangle, and notice that the upper function changed for your height. So, for the first one in red, this one right here, the upper function is determined by the reciprocal function. When we get down to the green box, the upper function is now determined by x equals 3. Because we have a change in the upper function, that's going to require two integrals. Okay. Now the distance from the green represented rectangle to the axis of revolution is also going to simply be y. It's the upper functions that are different. So h of y is equal to, now our function 1 over x, okay, 1 over x determines the distance from the x-axis to this point here on the graph, okay? Now, if we solve that for y, that's going to be x is equal to 1 over y. And 1 over y describes the distance from here, well, let's do up here a little bit, from here all the way to this point here on the graph, okay? So it's going to describe that distance. So when we're talking about h of y, okay, it's going to be 1 over y, and then we need to subtract out that gap, which is 1. So it's going to be 1 over y minus 1. Okay, volume for the upper portion is going to be 1/3 to 1, and the distance from the represented rectangle to the axis of revolution is simply y. The height of that represented rectangle is determined by 1 over y minus 1 dy. Okay? And then we need to do the second integral. This should be an equals. This should be a plus. And we're going to do the bottom portion there. So 2 pi integral from 0 to 1/3. And actually the bottom portion is simply a rectangular piece, so that's going to be pretty nice. So it's going to be 2 pi integral from 0 to 1/3, and the height is going to be a distance of 2 the whole time. Okay. All right, so that's going to be 2 pi integral from 1 to 3 of 1 minus y dy plus 4 pi integral from 0 to 1/3 of y dy. So 2 pi y minus y squared over 2, evaluated from 1/3 to 1, plus 4 pi times y squared over 2 from 0 to 1/3, and we'll go ahead and we'll go on to the next page to go ahead and integrate that. I'm not integrate it, but evaluate it, pardon me. Okay, so 2 pi 1 minus 1/2 squared minus 1/3 minus 1/3 squared over 2 plus 4 pi 1/3 squared over 2 and then minus 0 squared over 2 So it's going to be 2 pi, 1 minus 1/2 minus 1/3 plus 1 over 18 plus 4 pi times 1 over 18 equals 2 pi, get a common denominator, and that ends up being 4 over 18 plus 4 pi over 18. So that's going to be 12 pi over 18 as the volume, or approximately 2.0944 units cubed. And of course, you can reduce the 12 pi over 18 as 2 pi over 3. Okay. So this one, the shell method, was a little bit more difficult because we needed to use two integrals. Anytime you have a change in your upper function or your right function, or your left function or your lower function, you got to use a second integral. Okay, let's go ahead and take a look at the same figure, and then we'll determine if we need to do the disk or the washer method. Okay, so again, we'll sketch the region. Again, it's not the scale on the y-axis is the same as the x-axis, but this is just so it's a little bit clearer to see what we're looking at. So there's a region. We're going to use the disk method because there is no gap or cavity between the axis of revolution and the figure to be rotated. So we're going to do just the disk method, and disk method, your radii are perpendicular with the axis of revolution. And so that's up and down, so that's going to be a function in terms of x, and that's simply going to be the height 1 over x. So that's your radius function. Volume is pi, integral from a to b, r squared dx. So we're going to be integrating on the x-axis, along the x-axis, so pi, integral from 1 to 3, 1 over x quantity squared dx. So that's going to be pi, integral from 1 to 3, x to the negative 2 dx. So pi, add 1 to the exponent, negative 1, divide by the new exponent of negative 1, and evaluate from 1 to 3. So negative pi, 1/3 minus 1, so that's going to give us that negative pi times negative 2/3, and so that gives us that 2 pi over 3. And again, the decimal approximation. Okay. And so you can say that, I would say that in this case, the disk method was going to be the easier method. So it really depends on what the region is, what functions you're using, which one is it easier to solve for, the x or the y. That'll kind of dictate which method you're going to use. Again, one of the key elements is to sketch the region. What's the axis of revolution? That can really help with visualizing everything. Without that sketch, it is a little bit more complicated to get everything straight. And then, of course, if you're doing both methods, integrating with respect to x and with respect to y, to find the volume of the same thing, you should be getting the same volume each method. Okay. Alrighty, so that concludes this video, and we'll see you next time.